I'm recording. Okay, but okay, we're at 4 p.m. now, so we better get started. Let's continue. Okay, so we are picking up where we left off, where we were talking about vector space previously, right? A lot of you guys are making jokes that this now is become a course of linear algebra. It's only for the first lecture, and after I say a few words, we will start to talk about Hilbert space already. It's still linear algebra, but Hilbert space is more directly related to quantum mechanics, and this is where we see all the weird symbols that you mentioned last time. But let us recap what I was mentioning last time, is that what qualifies to be a vector space. So vector space is any set which we call V, and we need to have a few operations among its members in order to qualify as a vector space. So firstly is the scalar multiplication, right? Okay, so scalar multiplication is if you have a vector, if you times any scalar, it becomes a new vector. And if you're talking about R3, the scalar must be a real number. But later when we go to quantum mechanics, it could be any number, complex number or real number, anything you can multiply to a vector, right? And then you also need to have addition among members, right? So u plus another vector, it will give you another vector. And then we got the inner product. So we take one vector u with dot product with another vector v. And I introduced to you this symbol. The reason will be clear later, because it's going to be very useful in quantum mechanics. It is just this vector times this vector, right? And also you can write it in matrix form. So if these two are column vectors, what is actually happening here is that if you're talking about R3, right? So if you're talking about R3, is U transpose times the V, right? So this is an example in R3, okay? And we call this the dual of U. Okay, so the U is a column vector. If you take the transpose, it is the dual vector. This is what we know from the Newtonian mechanics. I will tell you what happens when we talk about complex numbers later. But for now, let's continue on. If you have a vector space, then you can define a set of basis vectors, right? So if my vector is n dimensions, then I have n basis vectors. So we call this basis orthonormal basis if they are all perpendicular to each other and each of them have unit length. So orthonormal if the inner product between any EI times any EJ is the Kronecker delta. Okay, so this one also you need to pay attention. This Kronecker delta is something we will also use quite often. So Kronecker delta is like a it's a matrix. The diagonal term is equals to 1 on the diagonal if I equals to j, is 0 if I not equals to j. Okay, so this is what we call the Kronecker delta. Okay, so and then let me double check the system. Drawing tablet. Oh, I do have a drawing tablet, but my handwriting looks very ugly on it. And I don't like it. Yeah, because drawing tablet, there is a lag between what you do on the tablet and what appears on screen. So if you look at the screen and you write, right, your handwriting will come out different because there's a lag there, right? Because you're used to real life writing zero lag, and that's how your handwriting is formulated. But even like this, my handwriting is already not that nice. So imagine it gets worse. Now, for point number 5, we have operators. Okay, so operator is something that there's a mathematical definition, rigorous stuff and all that. But I guess for easy to remember is that operator is something that eats a vector and you spit out a new vector. So it eats a vector and then you spit out a new vector. Okay, but if the vector you spit out is just a multiple of the original vector, we call this an eigenvector. So if U is an eigenvector of A, then you eat the vector, what comes out is still U just times some other constant. Okay, so times other scalar. Just to like reassure everyone that this is nothing very special, let me show you an example. An operator in R2. Okay, so I'll just give you an explicit example of an operator in R2. It's just a 2 by 2 matrix. So an operator in R2 that rotates, I will give you this operator that rotates vectors by 45 degrees. Okay, so this operator is given by 1 over, it's a matrix, 1 over square root 2, 1 over square root 2, 1 over square root 2, 1 over square root 2. Okay, so to show you how it rotates, right, let us apply this on the unit vector I. So if you do this on the unit vector I, okay, 1 over square root 2, right, unit vector I is just 1, 0, right, remember? So if you times this, what do you get? You get 1 over square root 2, 0, and then you get 1 over square root 2, right? Okay, so what you have here is that originally, right, originally you have the vector that is unit vector I, okay, and then it becomes 1 over root 2, 1 over root 2. So the x and y component are the same. The square root 1 over root 2, it will make sure it's still a unit vector. So what happens is my unit vector has been rotated to 45 degrees angle. So this is my new vector, so I just call this E, and I have been rotated by pi over 4. Okay, so this is an operator. This is not the eigenvector, right, because the direction has changed. So this operator eats the unit vector and changes it into a new vector that is pointing this way now. Okay, so that is my operator in R2. Okay, so yeah, so that is basically the basic notions of vector spaces. Linear algebra 101, the crash course. But you guys already learned linear algebra, so in a slightly different setting, right? But now what we're going to do is to go to quantum mechanics now. Okay, so any questions so far? Yeah, that's true. Yeah, handwriting with mouse. So even your tutorial presentation, I don't know if anyone would consider doing handwriting with mouse. If you have not tried it, right, you do it on Photoshop and see, like, you try to write something with a mouse on Photoshop and see how it looks like. Actually, there's still space here, so should save the environment. Do not waste paper. I will continue here. Let's go to section 1.4, the postulates of quantum mechanics. So now we start to talk about quantum mechanics. All right, no more linear algebra 101. We are PHY 202 now. Okay, so why do we spend time recapping vector spaces? Is because everything in quantum mechanics happens in Hilbert space. So with Hilbert space, usually people write it with a curly H. We call this Hilbert space. It's named after David Hilbert. He's a famous German mathematician who is working around the same time as Einstein and friends with Max Planck and all those people there. Okay, so Hilbert space is a vector space with complex numbers. Obviously, for the math people who are here, this is not a very rigorous definition, but remember that, you know, most of us in physics have not learned the concept of algebras, numbers, and fields and all these things yet. But in order to use, for the purposes of quantum mechanics, just remember it's like vector spaces, like this kind of thing here, but with the extra thing that we can also use complex numbers. There's another extra thing that makes things worse. The dimension of the vector space can be infinity, but we worry about that in chapter 3. Okay, so for now, let us start with something very, very easy and very, very easy to imagine. Okay, so that is what we will begin with in our setting, our stage where quantum mechanics takes place. So let's talk about the postulates. The postulates cover different aspects of quantum mechanics. So one of the first aspect is about states and observables. Okay, so the state is kind of something I mentioned on Monday's class, like What is the cat doing? Is the cat dead or alive? That is the state. Okay, is the electron spin up or spin down? That is the state. What is the momentum of the electron? State. Okay, so all these are states. So the first postulate is concerning about the state of a system. So postulate one, right? So we also have postulate. Remember when we did special relativity, we have 2 postulates. Quantum mechanics have 5. But the first postulate says that the state of a physical system is given by a vector in Hilbert space. Is given, or maybe let's say represented by a vector in Hilbert space. Okay, so this is a Hilbert space. Now, as I said, right, when I have a vector space, I'm going to have a special notation for a vector, right? In R2, I write it in this way and stuff like that. So in Hilbert space, the vector I will write is this thing. We do it this way. Okay, why? You will see more clearly in the next few minutes, but this is a vector in Hilbert space. Okay, so a state is described by this vector in Hilbert space, and there is a special name for this vector. We call it a ket. Okay, why ket? Again, it will be clear in a moment. Right, let's continue first, unless some of you already can figure out. Okay, so that is a state in Hilbert space. So just now I say, right, Hilbert space is a vector space with complex numbers. So let's give a very brief example. Right, a vector space ket is let's say a 2-dimension. So two elements, but the elements can be a complex number. So let's take a complex number. 1 plus 3i is a complex number, right? And then 2 plus 4i, another complex number. So this is an element of a 2-dimensional Hilbert space. Okay, and in fact, this is what we will do quite often. This is in example 1.4.1. So let me bring up the PDF. Okay, so a 2-dimensional vector space is something that we will use quite often. So this is an example for a concrete physical situation, the state of an atom. Right? So in this example, 1.4.1, let me write this down first. We have an atom with only 2 possible states. So it's either, in this situation, we only consider a ground state, so lowest energy, and an excited state. Okay? So it can be described by these 2 vectors. So yeah, that is very, very simple, right? So we will start with some simple problems, starting from chapter 2. Okay, so this example talks about the state of an atom, right? So the ground state, we represent this as some ket. So the nice thing about ket is you can write anything inside, so that it's easy to understand what you're talking about. So you can just write G, right, or anything, and the ground state, it says 1 vector, and then the excited state. So let's use the letter E for an excited state. E is another vector, right? So that is the basic thing about the ket in Hilbert space. Okay, yeah. So far so good, right? Everything pretty clear. Was he against? I don't remember him being against, right? But they are they are both in Germany, so yes, maybe it's the same Hilbert you're talking about, because they both exist around the same time. Definitely they met each other many times. I think they're in the same university. No, I'm not sure now. I forget. Yeah, Göttingen, I think, in Germany. Oh yes. Not to say against lah, but the incompleteness theorem came about is Hilbert gave a famous speech, right? He outlined like 100 mathematical problems that will be solved, that is interesting to solve, and Hilbert's original vision was that the entire of mathematics can be reduced into a set of axioms, and you can prove all the true statements from the basic set of axioms. It's kind of like theory of everything for physics. It's like quantum gravity for physics, for mathematics. But Hilbert proven that is impossible. Right? So if you want to, there are some statements that are true, but you cannot prove from existing axioms. You need to add axioms. But when you add more axioms, you get more true statements that cannot be proven. So no matter what you do, you can't achieve Hilbert's vision. Right? So it's not Hilbert was against it, but it was opposite of what Hilbert expected when he originally gave the vision. Where was I? How come I'm talking about Gödel? So now remember, a vector space has a dual. So in this sense, we also need to, I will show you how to write the dual of this. Right, so a state, right, we call this psi, right, and this is a ket. It has a dual. Okay, so instead of I write the transpose symbol, I call this psi here, right, and this psi here is given the name of bra. Okay, so the dual operation, so the instead of transpose, right, the dual operation is written as if I have the state ket, if I want to take the dual, that I will use this symbol, right? We call this the dagger because if you the latex one, they draw it really looking like a dagger. Okay, so the dual of this will be written in this symbol. Okay, so this is what the dagger. Okay, so let's take an example. So this dagger operation, right, the dual means is the following. So let's take an example. If I have a two-dimensional vector, right, so something like this, a two, it may be describing an atom either in a excited state or a ground state, so I write something like this. Okay, so this is the ket. If I want to take the dual, it means I do this. All right, so if I want to find the dual operation means you take the transpose just like R2 and R3, but now we have complex numbers, so there's something extra, so you need to do something extra. So it's transpose, and also complex conjugate. Okay, so after transpose, you're not finished, you need to complex conjugate everything inside. So what you get here is psi, that is the bra, the dual of this, and then the transpose, so it becomes a row vector now, and you need to complex conjugate everybody, so it's 1 minus 3i, 2 minus 4i. Okay, so it becomes a row vector, and every number here is complex conjugate to the original one. Okay, clear? Easy, right? Transpose plus bar, yes. Yeah, the star symbol. Yeah, I talked about this last time. Complex conjugate, right? So Z is A plus IB, right? So the Z star or Z bar is A minus IB. Okay, so actually, in fact, the star is where a lot of physics textbook use, but a lot of math textbook use bar, but sometimes people, some math people do this and some physics people do the other way around. It kind of depends. The dagger, the dagger, yes, the dagger, yeah, so that's why there's a confusion, right? The dagger. So why need complex conjugate? So the reason is it is an operation we define, right? So we purposely define it this way so that a lot of other quantities can be easily calculated later. But in particular, the reason why complex conjugate is that even though we have a vector, right? I have a vector, and therefore normally people like to imagine the length of the vector. But now we are in complex number. So what does it mean by length? So maybe you can still calculate something related to the length, which you call the norm, and you need to do the complex conjugate so you get a positive number that is not complex, right? So the norm, you end up to be a real number. Okay, so yes, the length, so is here. So before that, right, we need to define the inner product. So inner product, so let's talk about inner product, and I guess it's best to start with some concrete examples, right? So let's say I have this vector, so 1 plus 3i, let's take the same as just now, and let's take some other ket, another different vector, so let's take 2 plus I and I. Okay, so the dual of this, so you said in math it's called a star, but we call this the dagger, 1 minus 3i, 2 minus 4i, and then I can take the inner product between these two vectors. So it's the same as what I said last time for the vector space. I take one of them to be the dual, and then I times them together. Okay, so the inner product between psi and phi is, that's why we call this bra and ket, right? So we write it in this way, right? So it looks very nice. It looks like you're taking this, and then like Tetris, this is like playing Tetris. So one of them, you join them. So this is like Tetris. And what is actually happening here is 1 minus 3i, 2 minus 4i times the row vector times this vector. Okay, so if you multiply this out, right, so this is going to be 1 minus 3i bracket minus 2 plus I, and then 2 minus 4i, and then times I. So if you work everything out, I guess I'll skip to the answer. You get, let's see, check my notes, 5 minus 9i. Oh, sorry, plus. Okay, 5 plus 9i if you expand everything out. Okay, so this is how you get the inner product. So inner product, you got this between two different vectors. Okay, but notice that this is a complex number. So let's see what happens if we try the other way around. Okay, so let's take this now and then do this. So how do I get this? Well, let's take the dual of this. So the dual of this is minus 2 minus I and minus I. Am I right? Okay, so we got this now. So let's see what happens if we times the two together. What was it? Minus 2 minus I minus I, and then column is 1 plus 3i, 2 plus 4i, right? So row times column, negative 2 negative I, 1 plus 3i, plus negative I, 2 plus 4i. So if you calculate everything out, you're going to get 5 minus 9i if everything works out correctly. And notice that they are not the same. They are not the same, but it is the complex conjugate of the previous answer. Of psi phi. So generally speaking, this is the nature of inner product with complex number vector spaces, Hilbert space, right? This is different from our Newtonian mechanics real vector space, because generally, right, if you take this inner product and you take the complex conjugate, you get phi psi, the other way around. So this is kind of like Tetris also. You in Tetris you can flip your thing around, right? So you do a complex conjugate, you flip the thing around. Mathematically here means taking the complex conjugate. Okay, so and now we see why this is called the bra-ket, because you see the one that is pointing this way is called the bra, the point, and then the one is this way, we call this a ket. So in total, the whole thing, after you join them together, it becomes a bra-ket, or actually it's an English word, bracket. Right, you add a C in the middle, it becomes a bracket. And this notation was invented by Dirac. And it makes calculation with quantum mechanics easier to understand. Because if you say that everything in the vector space language, it will feel like very abstract. You need to remember the definitions. You need to remember what is this object, what is this object. But if you write it this way, oh, you know it's the dual. And then you write this way, you dual. Imagine defining everything with just letters, right? X, Y, Z. One of them is a dual, one of them is not. Is very troublesome. So you do it this way. And it makes everything way more convenient. Okay. Transpose is the noob version of dagger. Yeah, yes. Because yes. So actually you can, if everybody here is a real number, right? Then you take the dagger is only take the transpose because you have got nothing to complex conjugate. Okay. Yeah, so so this is the point where you've seen the flipping the bracket. Kind of, in a way you can think of it this way, right? We are establishing the rules of the game because remember what led us to do this? It is kind of forced upon us from the experiments that I discussed on Monday's class, right? Like, because you cannot use Newtonian mechanics to describe the motion of a particle. You cannot use R3 anymore because the particle, you know, you got electron passing through slits, it can interference, and then sometimes if you observe it, there's no interference. If you don't observe it, you got no interference. So that's why, right? That like using R3 vector doesn't cut it anymore. So we have to design a new set of vector space that can capture all these phenomena. That is, we say design, but it's already a pre-existing vector space that Hilbert already considered, and other people around that time. So yes, in that sense, we are establishing the rules of our game, right? So we are like designing the rules so that it will later, as we cover more and more postulates, it will see how we capture our experimental results, right? So it's like not doing things randomly. Is the main reason why, like, the people Hilbert, Planck, Einstein, Schrödinger, they tried many things, and this is the one of the thing that works to describe the experiments, and then we will spend the rest of the course studying all the different phenomena using this vector space. Okay. So just now I said we want to talk about the length. So this is, we call this the norm, right? The norm of ket is, well, the norm, right? So psi, what is the norm? In R3 we know this as a length, but we can do something similar, right? So we take the bra-ket on itself and then the square root. Okay, so that is the that's basically just the norm, right? So if you take a vector and then you take a complex conjugate, right? So let's take an example, A, B, right? If you take the the dual, you got this and this. So you notice that if you do this, right, it's just A bar, B bar, A, B. Then you just get A conjugate A plus B conjugate B is basically the modulus of A square modulus of B square. So this is a real number. So this will ensure that in Hilbert space, vectors still have a real number norm, right? This, if you don't do the complex conjugate here, you will get some other complex number here. Okay? Yes. So yeah, you can. Actually, there are things like cat, cat. There are things like this, but it's not in our course. There will be more complicated things. It will be like a tensor product. But in our course, we will discuss this. A cat bra. A cat bra is an operator, but we'll come to this later. Okay. So for now, the reason why the bracket is very nice is because yeah, you flip this, a vector, boom, it becomes a number. Like you hit a line in Tetris. So if everything you fit together, then it becomes a number. So two vectors turns into a number, and that's why I keep saying bra-ket is like playing Tetris in one dimension. So the next thing to talk about is the basis vectors, but it works the same way as vector spaces. Right, they are the building blocks of a vector space. So if my Hilbert space have n dimensions, then I just write the ket for the basis as well, e1, e2 until en. Right, and then they are orthonormal if ei bra-ket with ej is the chronicle delta. Okay. So yeah, so simple example. Let's take a two-dimensional vector space, Hilbert space. Right. So a standard basis will be just like this. So it's like exactly the same as R2 actually. The only difference is now you can use complex number together with this. Okay. So you can check, right? E1 inner product by itself, you get 1, and then E1 inner product with E2 you get 0. E2 E1 is also 0, and also as expected is actually the complex conjugate of 0. E2 with E2 you get 1, right? So chronicle delta. If they're the same number is 1, if they're different number you get 0. And any ket can be built, right? I call this built. Of course, the technical term is like a linear combination of the basis. So any ket can be some constant times the basis, the first basis, and another constant times another scalar times the basis. Okay, so this is like xi plus yj, right? And then you get ab. The only difference now is that a and b could be complex number. So it's actually not that big of a difference for now. Right? So now let us do a bit of a more heavy calculation. I will show you every step, since this is the first time we are doing this, but you will do this type of calculation quite often. So using this basis, we can calculate the inner product of any two kets or any two states, right? So let's give one example. Let's say the first state arbitrary, so let's say A1 E1 and then A2 E2, right? Let's stick with 2 dimensions, and then let's take another state psi. Let's say it's B1 E1 B2 E2. Okay, so what is the inner product psi phi bracket? So this one means I flip with the dagger, right? And then I combine with this. So flipping with the dagger means this becomes A conjugate E1, and then this is A2 conjugate E2, right? And then I combine with this ket over here. So it's B1 E1 B2 E2. Okay, then now it works the same way as all your mathematical rules. You expand the bracket. So expand the bracket means you multiply everything with everybody, right? So this times this I get A1 E1 times this I get E1, and then distribute to this, so I got A1 bar B2, this is E1 E2, and then this times this A2 bar B1 E2 E1, and then A2 B2, so it's E2 E2. Okay, but remember what we concluded just now. These are orthonormal bases, right? E2, E1, E1, E2, they are 0. So these two terms are 0. And then this is just equals to 1. So the, oh, I forgot B1 here. And then A1, B1 plus A2 bar B2, right? So this is like the dot product between two vectors. But this time, one of them must be complex conjugate. Okay? So in fact, in this basis, the norm can now be written as, well, I actually did this already. Let's do this one more time. Is, well, the norm is the square root of psi. So is the square root of A bar E1 plus A2 bar E2, right? And then you got A1, E1, A2, E2. Okay, so you got this, and if you calculate everything, you just get A1 square, A2 square, and then you take the square root. Right? Makes sense, right? So yeah, I hope you see now. It's very intuitive using the Bra-ket notation. It's like you're really imagining some Tetris block. You can flip it, and then the bra and the cat, if you do this, it becomes a number. What this number is, you calculate through this method, right? And so on and so forth. Okay. So this is page 3. We're only in page 3. Okay. Now, the basis, okay, let's put it this way. When I say Hilbert space with complex number, right, what is actually happening here? The cat is a cat, it's not a number. So it doesn't really make sense. It doesn't really make sense whether a vector is a complex number or not. It's a vector, right? What you can do is you can do scalar multiple. That is the complex number. So not to say that the Hilbert space can be a basis, because you can also say that I think you're referring to the numbers inside here. It can be complex. So I can define another set of, let's say, another set of bases I, 0, and need to be careful with the sign. So it can be complex actually. Is it plus or minus I? I think it doesn't matter. Yeah. So it can be complex. Does that answer your question? Does that make sense? Okay. The basis, the important point of a basis is orthonormal. In fact, orthonormal, the normal is an extra condition. Sometimes people use basis where the norm is not 1. Right? But as long as they're perpendicular to each other, then you can build any other vector from the basis vector. Okay, so from here, right, you can even write the same basis. So let's do this since we're here. I think, okay, so to make sure this is the same vector as this, is like minus IA, the new basis, minus IB in the new basis. Right, so you can, I think, yeah, if you multiply this, it will make sure that we got the same vector. Any questions so far? Yeah, I think so. Like you can put it this way, I guess. Yeah, so you can. Yeah, so the point I was trying to say initially is if it's a complex number, you can just think of it as a coefficient. Yeah, and then the rest of the vector is some vector. So it kind of makes no difference whether the basis got complex number or not. You can take it out and make it a coefficient. Okay, so we only talk about the state, right? What is the electron doing? Is it up or is it down? What is the cat doing? Is it dead or alive? But the next thing is about the observation. So the postulate 2, the full statement says the following. An observable property again, it sounds very abstract. It could be anything, and in fact it could be anything, but the common ones are going to be like the energy of the particle, right, or the angular momentum, or the linear momentum, or the spin, the magnetic dipole moment, and so on, right? So a lot of, like, basically all our physical quantities. Okay, an observable quantity is Hermitian. I will explain what this means. Okay, so Hermitian operator acting on vectors in Hilbert space, right? But now we are calling these vectors ket, plural, in Hilbert space. Okay, and then there's more statements here. I will explain each part of the sentence after this, after I finish writing, with a complete set. Okay, so complete set means something specific. I will explain this, of eigenstates. Okay, so I'll explain this, but let's start with operator, right? So this is an operator just like what I mentioned earlier. It is an operator that eats a vector, but now we're calling this ket, and then it spits out a new ket. Like I said, in my own mind, I was thinking, when I learned this for myself, I say shit out a new ket, but it sounds too bad to be in a lecture note, so I say spit out. Okay, so it spits out a new ket. So let's talk about, so let's take an example of an operator. It's still, the simple example is still some kind of matrix, right? A, B, C, D. Okay, so let's say this operator eats this ket. Let's put this as alpha, beta, right? So it could be any complex number here. We have seen this earlier already for R2, but now this could be complex number. Okay, so this eats a ket is basically the same like doing this in this particular example. So it's alpha, beta, and I think everyone knows how to do this, right? It's just A alpha plus B beta, C alpha plus D beta. So this is a new column vector, and this is what I would say, this is a new ket. Okay, so a new ket. So let's give this phi. Let's call this phi, right? So that means A acting on this is a vector. So next time you can just think of this as a ket. This is the new ket that we are talking about. Okay, so let's take the dagger. Let's take the dual of this new ket. So I forgot to tell you what the official name of the dagger. It should be called the Hermitian conjugate. So this is what I said, dagger. Yeah, this is the official name, right, of the dagger operation. The is, okay, so let's take the dagger. So I got this, right? But let's look at the result. It's basically the complex conjugate of everyone here, right? So it's complex conjugate of everyone. So it's A bar alpha bar plus B bar beta bar, and C bar alpha bar plus D bar beta bar. Okay, but actually if you think about it, right, this is also like a result of a matrix multiplication. This is like taking this this row vector, and then you times it with this column vector. So C, right? and then B, and then D. Right? So if you times it, you get this correct combination. Right? So that means, and then also at the same time, I was saying that this ket phi is equal to A times this. So this is actually the Hermitian Hermitian conjugate of this operation, right? And then we recognize that this is the bra of the original vector, and this is another operator, so we will call this the dagger of A, right? So this suggests that, remember, like was it Kaishen who said, yeah, we are establishing the rules of the game. So now we see this, we add a new rule. This suggests the Hermitian conjugate of A is Hermitian conjugate is also the same thing as before. It's still taking the look at this, right? Is the transpose, and then you bar everybody. So it's transpose complex conjugate. So we call this A dagger. Okay? Make sense? Let's see where we are now. Okay, so there's a few more things to talk about, but I think should be probably a lot of new information. So let's take a break, right? So let's take a 10 minutes break. And we continue at 5:08. Okay? Yeah, so let me stop the actually, is there any question? Okay, I'll read the question. I'll stop the recording first to save the space, hard disk space. Start recording. Okay, full screen. So we are still talking about postulates, right? So we know that postulate 1, a state of a system is a vector. Then if I want to talk about, we're still talking about this halfway, right? So I just explained to you how does operator work in Hilbert space. But if you want to talk about observable quantities, it cannot just be any operator. It must be a special category, a special class of operators, which we are called a Hermitian operator. So what do I mean when I say an operator is Hermitian? So let me explain it here. Am I sharing screen? I am. Yeah. Back to pain. Yeah, it's like taking the medicine, and after that you will see how everything works, and it's gonna, at least to me, because I told you about my friend last night. It's like, wow, everything feels very cool when you're able to do the things that we will learn how to do later. Okay, so what is an Hermitian operator? An operator is called Hermitian if you're doing the dagger, you give you back the same operator. Okay. Well, I'll give you an example of a Hermitian operator. Let's take an example of sigma y. So later you will deal with this quite often, right? So let's just call this sigma y, or if you're not comfortable, let's just call this A. But I'm just giving you an example of a Hermitian operator. So let's take 0 minus I 0. Okay. So this is something that we will encounter later, but I'm just demonstrating this Hermitian property. Hermitian property means dagger, it will be the same result. So dagger means what? You take the transpose, right? So if dagger means I transpose this matrix, this is 0, this is 0, transpose this I, and then you take the complex conjugate, and then you got minus I again, I here again is the same. So it's the same as the original one, right? So you come back to the same original operator. So this is what we call a Hermitian operator. Okay. Now let's talk about the ket bra. So if I am given two cats, so let's say psi and phi, we can build an operator out of it. So operator, you do a ket bra, right? Instead of a bra-ket, you ket bra, right? So the bra-ket, when you join them, it becomes a number. But if you do it the other way around, the ket bra, it becomes an operator itself, right? Why is it an operator? It's an operator because it eats a vector and shade out a new vector, right? It's an operator because it eats a ket. So let's take some other ket. So let's call this alpha. And what happens if I eat this ket? So A eat alpha. So A is equal to psi. So it's psi, phi, and then eating alpha. So this thing becomes a number, right? So this is a number. So it's just a number times a vector. So this is, it spits out a new ket. So it's an operator. Okay. So let's take an example written in a basis. All right. So let's take a slightly more concrete example. So let's take A1 E1, and then A2 E2, right? And then I take another phi, so I take B1 E1, and then B2 E2. Okay. So I can do this operation. I can build an operator out of this. Okay. So let's look at this. So I need to dual this. So dagger this. So I got B1 E1, B2 E2, right? And let's see what happens if I do this. So doing this means you just multiply, right? So multiply. So I got A1 E1, A2 E2, and then times B1 bar E1, B2 bar E2. So you just multiply everything out. Okay. So yeah, just do everything step by step. So I got A1 B1, E1 E1, and then this times this, I got A1 B2, E1 E2, and then this times this, so it's A2 B1, E2 E1, and finally the last two, A2 B2, E2 E2. Okay. So notice that E1 is remember E1 is something I usually write this, and then E2 I usually write this. Okay, it's just the basis vector 0, 1, 1, 0. So if I multiply this together, right, this is now a column times a row. So I think I'll just save time. You can work it out yourself. But in the end, it becomes 1, 0, 0, 0. And then this one becomes, right, if you work it out, right, it becomes 0, 1, 0, 0. And then this becomes 0, 0, 1, 0. And the last one is 0, 0, 0, 1. Right. So this is a sum of matrices. So if you add everything up together, I get A1 B1 bar, A1 B2 bar, A2 B1 bar, A2 B2 bar. This is B2. Okay. So if you do this, right, yes, you get a matrix, which is what we interpret as an operator, right? A matrix times a vector, a column vector, you become a new column vector. Okay. So yeah, notice that my yeah, I guess you know, right? What? What's going? Oh, yeah. Yeah, thanks, Gloria. I will introduce to us our notation uh, soon, right? So you see, you can, and I will compare and contrast the two. Okay, so um, so let's see. How much time do I want to spend? Yeah, so an operator, and so what we have learned about postulate 2 is that an observable quantity, if you want to observe a physical quantity, it needs to be represented by an operator. And then let me show you the postulate, right? It's a Hermitian operator acting on vectors with a complete set of eigenstates. So that comes to the next part we are talking about. An operator will have an eigenvector. Okay, so a Hermitian operator will have its own corresponding eigenvectors. Okay, so that is the content of the next example. Okay, so this is the preview of chapter 2. I guess I definitely will do this example since you say it's too mathy. Well, here's the physics part. This is a preview of chapter 2. Okay, so in chapter 2 we are going to measure the spin of an electron, right? So let's not worry about the details for now, but just remember when we talk about spin, right, there is a rotation direction clockwise or anti-clockwise, and then there's an axis of rotation, right, and the direction will be the direction of the angular momentum. So this is one state. Spin is pointing up, so I'll just use the up arrow symbol, and this is one basis. Okay, and then in another situation, the electron could be rotating the other way around, right? Instead of clockwise, it's rotating anti-clockwise, so my rotation direction is pointing the other way. So this is another possible state, right? Whether it's clockwise or anti-clockwise. Okay, so this is something that can be measured. So this can be measured. We'll talk about this in chapter 2, but this can be measured. But for now, in terms of postulate, right, if something can be measured, then I need to know what is the Hermitian operator. So there's an Hermitian operator. And because it's in chapter 2, I can't really tell you yet, so I'll just tell you the answer. The operator is given by this. Okay, so the operator is given by this. Okay, and then let's see what happens if I add these operators onto this. These are eigenstates, right? So these are actually the eigenvectors of this operator. Right? The eigenstates correspond to the states. Kets, right? Or eigenstates. Postulate 1 states are kets of this particular operator. So we can check easily, right? This operator acting on the up arrow is basically 1, 0, 0 minus 1 times 1, 0. What do you get? You just get 1, 0, right? So you come back to the same thing, right? 1 times 1. So the eigenvalue is 1, right? So is 1. Okay, so you can try on the other one. The other state is 1, 0, 0 minus 1. You act on this state, now you get 0, negative 1. So this is actually a minus of this. So this eigenvalue, so I'll just call this lambda down, is negative 1. Okay, clear so far? Am I recording? Yes. Yes. Okay. So this is now showing you how things work, right? So when you want to talk about discussing some physical system and then you want to know what state it is in, so there's going to be an operator, and the different states are the eigenvectors of the operator. Okay, so this is quantum mechanics, right? So let me repeat just to make it even more clear, right? So in a quantum system, right, whatever object, the motion of particle, whether the cat is dead or alive or whatever things, right, you want to measure something. Okay, in this example I want to measure the rotation. So if I want to measure something, there's going to be a Hermitian operator. Okay, so what does the Hermitian operator measure? Well, they will be described by the eigenvectors. Okay, what does this measure? It measures whether the electron is spin up or measure in spin down. And this happen to be, well, not happen to be, it is the eigenvectors of this state. And then when you talk about measurements, the eigenvalue is what we call the experimental outcome. So when you do something during an experiment, right, the reading will come out, right, in the whether you're using a machine or something, the reading. So the reading will come out as +1 or -1, and that is what we talk about when we refer to the eigenvalue. Okay, so the eigenvalue is the measurement outcome. So if the reading tell you +1, the machine tell +1, you know that the electron is this way. If you do the experiment, then the machine tells you down -1, that means your electron is doing this. So that is what we mean by the eigenstates and eigen measurements. Okay, so one last word to explain on the postulate 2. Okay, so it's not just eigenstate, but this set must be complete. So what does complete mean? So I shall explain now. Okay, so now, so let's talk about this. Let's take this as an example, right? So these two are can actually serve as a basis, right? So the eigenvectors how to say, can be work as a basis, right? Because psi1 is 1 0, and then ket down is 0 1. Okay, and a basis is complete. So that is what I want to explain, right? What do I mean by a basis being complete? So if the following holds, so more generally, right, so I got E1, E2, and all kinds of bases. So it is complete if this condition is satisfied. So the sum from the first and last basis, I take each basis, I make it into a ket bra, and then if I sum this up, I get an identity. Okay, so this might look a little weird, but it's actually should be very straightforward if I take this example. Okay, so if I take this, I get 1 0 0 1, and then if I take this, right, down, the ket bra, I get 0 0 0 1, and then notice that if I sum this up, right, so this plus this is just 1 0 0 1, and what do you get? The identity matrix, right? So the identity matrix. So therefore we conclude that that the eigen states of this operator, right, we need to refer to what operator we're talking about, because yeah, we are measuring something. Given an experiment, you can measure so many things about it, but we are particularly measuring the spin of this. So the eigenstates of this, we check that they form a complete basis set. So that is how the wording, yeah, that is what it means by complete. Okay. 1000. Oh, I accidentally put a 1. Yeah. So yeah, the eigenvalue here is a bit abstract. So I explained the machine example, but it's not always the case. But let's say you machine, then they give you a reading, right? So they tell you the number. So maybe this machine tells you the dial, they give you +1, then you know what the electron is doing. If you measure it, you get -1, then you know it's down. So the eigenvalue is just some number or some value. But to have a more concrete example, right? The ground state of the electron. No, ground state of the hydrogen atom. Right? So you can is by, we are measuring the energy of the hydrogen atom. So usually we call the symbol H, and then let's say the ground state, so I'll just call this G, right? But more precisely, we will do this in a later chapter. It's going to be the ground state, so it's 100, right? And then the eigenvalue is 13.6 electron volts. You already know this from modern physics, right, with Prof. Ong. So this is the eigenvalue, 13.6 electron volts. So they just tell you the value of the energy itself. Okay, any question? Okay. Now there's a few more details to take care of, right? So if you're feeling the pain now, all I can say, yeah, just bear for it, because once we learn all these things, we after this we'll make use of it, and it will feel very satisfying, right? Let's put it this way. Okay. Actually, what I'm going to talk about is already true in Newtonian mechanics, because a basis is not unique. A basis is just one way yeah, it's just a way to describe a vector. Okay, so let's take an example in R2. What am I talking about? Because in R2, right, a vector is a vector, is this vector. Okay, but your x and y coordinate is actually a choice, right? It's a choice made by the person, made by you. But whatever the physical system is, if the object is moving at this velocity, the vector is there, is the physical quantity. The choice is dependent on you. Okay, so for example, if you choose a basis ij, right? So ij means I take the horizontal axis, so this is my x coordinate, and then this is my y coordinate. So my unit vector along this direction is I, and then my unit vector along this direction is j. So therefore, let's take a random example. Let's say the length of this vector is 5, so this is going to be 5 over root 2, and then this is 5 over root 2. So in this basis, my vector is 5 over root 2 I plus 5 over root 2 j. Am I right? Okay, I think everyone knows this. We did so much of this last year in mechanics, even in EM, right? But we can make a new basis. Okay, so let's take a new basis vector. EI is the I rotated clockwise by pi over 4. Okay, and then so E1I, So I already give you this example, right? So it's 1 over root 2 minus 1 over root 2, 1 over root 2, 1 over root 2, and then acting on this, I get 1 over root 2, 1 over root 2. So this is 1 over root 2 I plus j. And then you do the same thing for E2. So you do the same thing, you operate on this vector, right? You get 1 over root 2 minus I plus j. So now the same vector can be expanded in a different basis. So this is the same vector, right? So this vector v doesn't change. Okay, v is still v. But now I rotate it this way. So now my vector has been rotated along this direction and this direction. And my basis vector is E1 here. And my basis vector is E2 here. Okay. So now in this basis, right, my v is written as is just 5e1. Okay. So just looking at the components, this is one of the things where we must be careful, right? Just looking at the components is actually not enough. You must remember that this number depends on your choice of axis. Okay. You guys have kind of indirectly done this before in mechanics. Remember that when you're doing Newton's law, a common question that you guys ask me is, oh, I do in the tutorial, I resolve my x in this way and that way, and then someone might ask, oh, what if I do this way instead? And then my reply is always the same. You get the correct answer, right? Doesn't matter whether you resolve horizontally or you resolve diagonally, because the vector is the same vector, so of course you're going to get the same answer, right? So it's actually the same thing. We are kind of like, when we are doing mechanics, it's a bit under the surface, but now it's going to be slightly more important when we are doing Hilbert space. Okay, so is everything clear so far? Oh, yeah. Yeah, this is not a rotation operator. It can have more than one. Yeah, it definitely can have more than one, because in fact, in the example just now, right, I written sigma z, and then there's even earlier there's a sigma y, because actually there's a sigma x, y, z. There's 3. So you definitely can have more than one. Okay. So what we have here is that I'll say this now. I know there's more questions, but I'll say this now before I forget. The basis is this stuff here, right? And then the components is 5 over root 2. Vy is 5 over root 2. Okay. Then both of these together will describe this vector. Okay. But here, right, I use a different basis. And then the components is also different. Let's call this V1. So V1 is 5. There's no second component here because it's purely in this direction. So V2 is 0. See? Different bases, different components. Different bases, different components. But at the end of the day, they're still describing the same vector. Okay? So, yeah. So that is the thing I want to emphasize at this stage. Yes, everything is still linear transformation. Yeah. Because eventually quantum mechanics is an application of linear yeah. MET 2. Actually, be glad that this is PHY, because Kaheng, have you taken linear algebra 2? You go even deeper, right? Linear algebra 2. It's going to be way worse than what we are doing here. So And here, notice that I did not spend time doing proofs and things like that, because this is not a math class. And even for, we will do some, right? There's going to be some theorems. I will prove this later, but there's no, like, it's going to be very different if you're actually taking linear algebra 2. What time is it now? Yes and no. Okay, so this is actually generally true in every physics, even classical mechanics, right? When we are solving harmonic oscillator, you use Cartesian. If you're solving orbits, you use spherical coordinates. Imagine solving the orbits of a moon using Cartesian. That will give us trouble. So in that sense, the choice of basis is correct. But in quantum mechanics, right, this question is even more deeper and a bit more philosophical. It's going to be related to entanglement and things like that. Those phenomena depends on your choice of basis, because your choice of basis will determine your measurement outcome. So it's even, and so what you said is true here, but in quantum mechanics there's an extra layer that is the quantum mechanicness of everything, like your measurement, things like that. You know, like quantum entanglement, right? The quantum entanglement is like the spooky action at a distance. We will talk about this towards the end of the course, but the details of this entanglement phenomena depends on both sides choosing the correct basis. If both sides chose the wrong basis, no entanglement. Okay, so that, I guess I'll keep it like this. I'll leave it at this for now, but this is also another reason why I emphasize basis choice, because there's an extra layer of factors that will influence phenomena. Not really, not really. In a sense that ruler is a local measurement. So kind of yes and no lah. Yeah. So it's not ruler, but more like directions, right? This direction or two directions here. So for entanglement, if the two distant people use different directions, then you cannot get entanglement. You must make sure they get the same direction. Or vice versa. I forgot already, but we will cover this in detail in the final chapter. But for now, right, we must concern ourselves with this question. So here is a question. Okay, given a vector v, and a basis choice. So we are still using R2 as an example, right? So given a vector v and a basis choice, so yeah, let's take the second choice, right? But let's say we don't know the components. So what are the components? Oh, another layer of complication, right? Not even entanglement, is the uncertainty principle. What I will show you later is that x and p are different bases of measurements. So if you transform from one basis to another, it's like checking x and then you look at p and then you get the uncertainty principle. So that is another different reason why bases are important here. Okay, so given a vector v, what are the components, right? So let's say there's a vector here and then the basis here, but how do you figure out the components? So the way to do it is by taking the dot product, right? So yeah, so the example is what is E1 and what is the thing that goes with E2, right? So the answer is, well, you take the dot product, right? So let's call this unknown V1 and unknown V2. Okay, so note the if I want to find V1, we dot with E1, right? So E1 dot V is going to be V1 E1 dot E1 plus 0. So that gives me V1, right? So in other words, V1 is E1 dot the full vector, okay? And then similarly, if to find the second components, you just dot with the second basis. Okay? So in other words, to find the jth right, arbitrary component, we dot with the corresponding basis ej, right? So this will give you Vj is just Ej dot product with the vector V. Yeah, don't be too dramatic. It's gonna be fine, don't worry. Okay. Okay, so yeah, some concept is new, right, and it's challenging, but you can't deny that a lot of things you're doing is actually is going to be kind of cool, right? Playing Tetris and things like that. So yeah, where were we? We are talking about figuring out the components. So I gave you this example in R2, but the same works for Hilbert space. Right? So let's say I have a state psi, and then I got the basis E1, E2, E3, E4 until En, right? Then I can expand this in terms of this basis. So this one can be written as C1 E1 coefficient 2 E2, right? So all the coefficients until Cn En. Okay, usually in quantum mechanics, like we know this somehow first, and the basis is based on the choice of measurement, right? So like the example just now, the basis is going to be eigenstates of this. So that's why this one is decided by what experiment you want to do. So what experiment you want to do will decide this, okay? And then this one is like, okay, the particle, whatever it is doing. So the coefficients is something that you want to determine. So to get so to get all the coefficients, C1 is just you take E1, then you inner product with the vector. Same thing for C2, you take the E2 inner product with this vector, and then same thing for everybody. Okay. So in this sense, right, we call this representation of the state in basis E1, E2, En. Okay. Okay, what time are we now? 5:35. Okay. Yeah, aside from saying you guys are dead, does anyone have any question to clarify? This is page 8. Okay, so yeah, we are talking a lot about linear algebra, right? This is a theorem from linear algebra. I'm not going to prove it, but it is going to be useful here. So we're going to make use of it. Okay, so this is from linear algebra. I don't know whether you learn it in linear algebra 1 or 2, but it says the following. Okay, so given a Hermitian operator A, okay, and it has eigenstates let's call this E1 En, right? So it has eigenstates E1 to En. So that means, right, if I act operator on any I, then it will come back to this times some coefficient, and these are what we call the eigenvalue. So E1 will have eigenvalue here, E2 will have its own eigenvalue, everybody will have their own eigenvalue, right? They may or may not be the same, but they're eigenvalues. Okay, so it has this. Okay, so these are my eigenstates. But it can be proven in linear algebra, which I won't do here. It says that it can be expanded. The operator A can be written, right? The fancy word is expanded, but it's just like let me write first. It's very hard. Somehow I cannot talk and write at the same time. Okay, so an operator is something that eats a vector and spit out another vector, right? And I told you that the ket bra can be written as a operator as well. And in fact, this is a sum of ket bras, j from 1 to n, e, j, the ket bra of corresponding states, and this is the eigenvalue, right? So it's the same thing. So lambda 1, lambda 2, lambda 3 here. So everything is can be expanded in terms of written like this. And this is actually like, yeah, you definitely learn the algebra. This diagonalizing a matrix. Right, so A is going to become lambda 1, lambda 2, and then the others are 0. Right? Yeah, this one is linear algebra 1, right? Yeah, you guys saying dramatic things. Yes. Yeah, we are still in postulate 2. Kind of. Actually, I already finished talking about postulate 2, but we are in between postulate 2 and 3. LA. Oh, is that why you post the picture of Liang? Because he is also LA. Right? But so like I said, it's like diagonalizing a matrix, but just to practice our Bra-ket notation, right, we can check, right? So because just now we said that, okay, if I take this EI acting on this, I will get by definition is supposed to be the lambda I and then EI, right? And then this theorem says that it can be written like this, so I can substitute this here. Let's see what happens, right? So AEI, so let's try to go from left hand side to right hand side. So let's put this inside. This is the summation of 1 to n lambda j ej ej, and then this operates on EI, right? So from this equals to this, okay? But this is a Bra-ket. Remember, we are playing Tetris. Bra-ket put together becomes a number. So this is actually a Bra-ket. So let me write out one more step. So this is EJ. This is actually EJ EI. And this is a basis, right? Orthonormal basis. So what happens to this one? It becomes a number, but what number? This number is a chronicle delta. It's either 0 or 1, right? So so this is only 0. This is equals to 1 if I equals to j. right? So I'm summing up over all the different j. I is some number, let's say number 2, right? So if you sum everything up, everyone 0 except number 2, right? So it's only 0 plus 0 only equals to the ith term, ei, and then the rest are still 0. Then we come back to lambda I ei. Okay, so this was proven in linear algebra using a different method, I know, but this is a good way to practice bra-ket, because in this course we will do stuff like this quite often. So it's a good way to show you how to practice this. Right, playing Tetris. You see, when these two things come together, it becomes a number. So always remember this. Right. So when we do later more and more calculation, you see, like Tetris, when you manipulate, you put these two together, collapse into a number, and then you other things put collapse into another number and stuff like that. So yeah, playing Tetris. Okay, what time are we at now? 7 minutes. So let me give you one more theorem, and this time we shall prove it. Okay. Yes, exactly. Yes. Not yet, not yet. We are halfway. We have 5 postulates, so we are still in between postulates 2 and 3. Postulate 3 is quite long, and then 4 and 5 is very brief. Okay, so I guess we will continue. We will finish chapter 1 on Monday. But let's do this theorem first. Okay, so let A be any Hermitian operator okay, or actually a Hermitian operator has the following properties. Okay, so the first property is the eigenvalues of A are real. I'll finish right first, but it's actually gonna be something interesting to relate to here. The eigenstates corresponding to distinct eigenvalues are orthogonal to each other. Okay, so the second one is a bit slightly technical, but the first one kind of like relates to something you mentioned earlier, right? It's like, how come complex number is supposed to be in our imagination, right? And then suddenly when we start this quantum mechanics course, I suddenly talk about complex number everywhere. Okay, but of course complex number is imagination because real life is real. What I mean is, when you measure an experimental quantity, right, your machine reading and things like that, they give you real numbers, right? The energy of an hydrogen atom ground state is 13.6 electron volt. 13.6 is a real number. So even though we are using complex things in Hilbert space, operators and things like that, and this theorem guarantees that our measurement still gives you a real number. Okay, so in one way to imagine, like in quantum mechanics, you know, we bring in complex number. It's like another alternate dimension, right? It's a lot of stuff happens in quantum mechanics, and then it affects our experiment that gives you real number. So a bunch of stuff happen in the complex domain, you know, whatever things, your quantum stuff, and then when you do your measurement, you come back a real number. But this quantum stuff affects your measurement. Okay, so this is why, right? So this is like we are using complex numbers at the same time with real numbers, but of course, like you said, real experimental outcomes should be real numbers. Okay, so this is why observables, experimental measurement must be represented by Hermitian operators. Okay, so that is the theorem. Yeah, so you must complete the sentence very quickly and say I have a cat, so that people knows you're talking about bra-ket. So let's give a the reason why I can give a proof here is kind of relatively simple. So let's denote the eigenstates of A by AI, and we're going to talk about distinct ones. So let's consider two different eigenstates, AJ. Of A. So what does it mean by them being an eigenstate? That means if A eats the cat AI, it will spit out AI back with the eigenvalue. So let's put the eigenvalue as AI, right? The little number AI. And then the same story happens here. If I eat AJ, the second one is eigenvalue come out and then AJ, right? So these are the eigenvalues. Okay, so I can very quickly prove this theorem by multiplying with the bra. So this is the reason why also we're proving this, is because it let us practice playing with the bra. Imagine cutting this sentence out of context, but I don't care. We are doing quantum mechanics. Multiply with the AJ bra. Okay, so this is AI, but let me purposely multiply with the AJ bra, the dual of AJ. So the AJ bra operator A cat AI, right? So we do it on both sides of this equation. So this is the AJ, and then this is AI, and then this AI. But remember, this is just a number. It's not an operator. So if it's a number, a scalar number, I can move it everywhere, right? Even for vectors, even for integrations and differentiation, I can move it anywhere I want. Okay, so I got AJ, AI, then this is my equation 1. So I'm going to do the same for equation, the second side. So I will multiply with the other one now. So multiply with the AI bra. So this becomes AI A AJ, right? The number I can put it anywhere, so I pull out the constant here, and then I got AI AJ. Okay, so this is equation 2. Now let's go back to equation 1 for the moment, and let's do the Hermitian conjugate. Well, everyone here is numbers, so let's take the dagger, basically the dagger, right? So let's dagger everybody. Okay, so if this one conjugate means I dagger everybody, so dagger everybody means you flip the order, and then you dagger this, and then becomes this, right? Conjugate means you do it this way, then dagger, and then here is AI dagger, and then you flip this, so you got AI AJ. Okay, but then, right, we started off saying that A is a Hermitian operator, so A is Hermitian, which is to say that AI, we are actually back to A again, and then this is AI bar, this is AI AJ. Okay, so I got my third result. Follow so far? Yeah. So like you say in a more compact way than the long speech I gave earlier just now. Okay, so now, right, let's do something interesting. On the right hand side I got AI AJ, and then on this side I got AI AJ, so I can just put these two equations together, right? So I'm going to take these two equations, and I'm going to take equation 3 minus equation 1. Okay, so equation 3 minus equation 1. So I'm going to get this. So if I do this, right, what I get here is, well, sorry, I meant the left hand sides are the same. See, AIAAJ, AIAAJ. The right hand side slightly different. AJ, AI, and then AIJ is here. Okay, right. So the right hand side is slightly different, but the left hand side are the same. So if I take the difference, it becomes this. Okay, so got AI, AIAJ minus AJ, AIAJ. So actually, they have the, I can factorize them. So I got AI. Sorry. AI bar minus AJ. Okay. So there's two possibilities. If I is equals to J, right? Then because these are the eigenstates of the Hermitian operator, so they are orthogonal. Okay, so if AJ equal to, so they are orthonormal. So AI AJ is equals to 1. Then this is equals to 1. So then we conclude that AI bar is equals to AI, which is to say that AI is real, right? J equals to I already. We are talking about the case where J equals to I. So when J equals to I, this is AI bar AI. Okay, so this is real. Okay, so we have proven the point number 1 already. Okay, so the eigenvalue is real. But if they are not the same, okay, so if they are not the same, then what we conclude is that yes, AI not the same as AJ. And then I got AI, AJ, I got this equation equals to 0. Okay. So if these two are distinct, and not, this term will be non-zero, right? So the only way to make this equals to 0 is that this is 0. Then that will guarantee it is orthogonal and distinct eigenstates. So this is before it gets too and more confusing, basically what we want to do is to show that the eigenstates corresponding to distinct eigenvalues are orthogonal to each other. Okay, so actually, as you might have noticed already, I did not close every gap in the proof because remember, this is still a physics course, right? The main reason why I'm showing you this proof is to practice playing around with bras and cats, right? And this is the sketch of a proof. Of course, there's all the cases that to be a real proof in math, you need to close all the gaps, which I haven't done yet, but at the same time, we are also towards the end of the class already, right? In fact, I overtime a bit. So yeah, so let's take which AIAJ. Yeah, so let me stop the recording and I will answer the question after I stop the recording. Okay.